In this video, we're going to discuss how to determine when an equilibrium will be reached. So when you have a reaction that will reach equilibrium, the problem is figuring out how far will the reaction go. Does only 1% of your starting material become product before your forward and reverse rates are equal? Does 99% of it become product before that happened? Maybe it's 50-50 in the middle, maybe it's 10,000 times more on one side than the other. Every reaction is going to have its own balance point, where your forward and your reverse reaction will be equal. However, for any particular reaction, there's an easy way to determine if you are already at equilibrium, or if you still need to react for a time, and which direction is going to be more reactive until you reach equilibrium. When you have a generic reaction, so some chemical with a coefficient plus another chemical with a coefficient in equilibrium with some products. Well, we can create what's called a mass action expression. The way this looks is our product to its coefficient times our product to its coefficient. So C to the C, D to the D, over our starting material to their coefficients. The brackets here represent concentration. For most of our work, that's going to be molarity. So it's a quick way to symbolize molarity without having to write the M in for all of them. And so this expression says that, hey, if I have a beaker and there's some amount of A in it, some amount of B, some C, and some amount of D. Well, if you could plug those values in for how many moles per liter, put them into this expression, do the multiplication division, that is going to equal some value. Well, you can put whatever concentrations you want together. As you change them, you'll get a different value. What it equals will be different for every mixture. So we call that Q. It's a quotient. It's a ratio. Our products are on top, our reactants are on bottom. This is a ratio of our products to our reactants. As we change how much, if we remove some of one chemical, well, that's going to change the value for that chemical, and so our Q value will alter as well. When you first start a reaction and you have nothing but starting material, well, the bottom is very large and the top is effectively zero. As time goes on, you'll use up starting material. And so A and B will get smaller as time goes on. They'll run out as you create more product. Well, this means our bottom gets smaller and our top gets larger. If you think about dividing, 1 over 10 is 0.1. But if you end up at 5 over 6, you're nearly at 1. If you keep going to 8 over 2, you're at 4. And if you end up at 10 over 1, well, you're at 10. As we change what's on top and bottom, the value they equal changes. And so Q alters as the reaction occurs. As our starting materials get consumed and produce more products, we will see Q change. Well, as long as our starting materials and products concentrations are altering, Q will alter. If you ever reach a point where your concentrations no longer change, then Q will no longer change. This happens at equilibrium. At equilibrium, concentrations are constant, so Q is constant. So if you could watch a reaction happen, and then you look again 2 minutes later and you see that the amounts are different, you would calculate out a different Q value. Watch it again another 2 or 3 minutes later and they've changed again, you have a new Q value. But eventually, you'll start watching and every 2 minutes later, it's the same concentrations, it's the same Q values. This is when you have reached equilibrium. That value The Q at equilibrium is called KEQ, the constant of equilibrium. It no longer will alter. Why this is important is that every reaction has its own KEQ. Not every mixture, every reaction. What this means is you can throw any amounts of A, B, C, and D together. They will always react until the Q equals KEQ. So if you have ever solved KEQ even once, you know what KEQ has to be for that reaction forever. Well, how does this change things? Let's look at a simplified reaction. Let's say it's just A goes to C. So I have some concentration of A to the first, I have some C to the first. If we are told that the KEQ for this reaction is 1.25, and at the very beginning, at time 1, we can look at our concentration of C, and we look at our concentration of A. So time 1. Let's say that there's no product and 10 starting material. Well, 0 divided by 10 is 0. You can't have anything we divide by 0. So Q right then would be nothing. But a little while later, I have removed some starting material and I've created some product. Well, 1 divided by 9 gives us a 0.111 for Q. So we have some product, and we have some starting material. And what we find is that when we do the math, when we actually take 1 divided by 9, it gives us a value, and that value is not KEQ. In fact, what this tells us is that the Q value, right now at time 2, our Q is too small. It is less than 1.25. It is less than the equilibrium value. What this means, if we look at the math, well, how do you get a small value? Have less on top and more on bottom. So right now we have a smaller value than we want. We have less on top in our division and more on bottom. To get a larger 1.25, I need more on top. If you increase the number on top of your division, you'll get a bigger number out. So I need more of C and less of A. I need this reaction to continue. I need more product. So we go to time 3. Maybe it's 8 and 2 now. And so if we did that calculation, 2 divided by 8 is going to be 0.25. It's closer. We put a bigger number on top this time and a smaller number on bottom, and my Q got bigger than the 0.111 before, but it's still not big enough. And so we keep doing this. This keeps happening for a while. 7 and 3, 6 and 4, 5 and 5. You get to 6 and 4 at some point. And if we calculate out some Q's, 0.25, 0.428, 0.66, 1, 1.5. What we find is, well, T5, T6. At time 6, I had a KEQ of 1. I had equal amounts of my product and my reactants, but I wasn't at 1.25 yet. If I had continued reacting all the way up to T7, oops, I would have gone past. 1.5 would be too much. What this tells me is that I actually stop reacting somewhere in between time 6 and time 7. I never actually reach these values for time 7. Because once you reach equilibrium, you can't change your concentrations anymore. And so you just stop there. And so the reality is it's probably a little bit like 5.5 over 4.5. that is 1.22, it's pretty darn close. We got a little farther, so a little past times 6, we made a little more product, a little less starting material, and we got very close to KEQ. What we're watching in this is we're seeing how Q alters as the reaction occurs. As A becomes C and our concentrations change, our Q value changes. But eventually it will reach the equilibrium value and there will be no more change in the concentrations. The reaction technically continues, it's just that A is converting to C at the same speed C is converting to A. What this lets us see, though, is our relation of Q. When Q equals KEQ, we are at equilibrium. When Q was less than KEQ, the reaction continued to increase product. There's a couple ways that this is said normally. We say that it moves towards product or that it moves to the right. The right side of the equation is usually the products. Those are all different ways to describe increasing the products. Well, if Q is greater than KEQ, we will move to increase reactants. If you think about why, if your KEQ was 1.25, as we just saw, but your concentrations at the moment were 6/4, well, we saw that one. It came out at 1.5. Our Q was too big. The top was too large. When I do the division, there was too much on top and not enough on bottom. The top is products. There was too much products. The bottom is reactants. There was not enough reactants. And so you have to remove some products and create some reactants to make the math when you divide come out where you want it to be at the 1.25. So by knowing my concentrations at this moment, whatever that is, if we were to look at time 1 or at time 4 or at time 3, if we just check, and there's a lot of ways to check. You can shine light into your solution. Different molecules absorb different colors of light. And so by knowing what color it absorbed, you can figure out which molecule you have more of and how much of it you have. Spectroscopy is a very powerful tool for monitoring things like this. So there's ways to do it. You can know how much of each chemical you have at any given moment. You can then use that to figure out, are you done reacting? Or does it need to continue to react? For any given reaction, we can create one of these mass action expressions. So for ammonia synthesis, well, it's our products, so the concentration of ammonia to the second power over the concentration of N2 to the first times the concentration of H2 to the third. All of that will equal Q. So let's take a practice. If concentration of N2 is 0.5, H2 is 1.7, and ammonia is 1.3. If we had the molarities for these, and we were told that the equilibrium constant is 49, what I want to know is, are we presently at equilibrium, or are we going to continue to react to create more products, or continue to react to create more starting materials? Well, how do we apply that? I've got my concentrations, and I have the mass action expression built from the balanced reaction. Well, if we want to plug those values in, ammonia was 1.3 to the second. N2 is 0.5 to the first. And H2 was 1.7 to the third. If we actually calculate out those values, 1.3 squared divided by 0.5 divided by 1.7 to the third, what we will calculate out is 0.688. This is our Q value right now. For these concentrations, my Q is 0.688. That means my Q is less than the target. It is less than KEQ. This means my value on top is too small, and my value on bottom, when I do the division, is too large. I need more of the top value, and the top value is products. So this will move towards products. It'll go to the right. We have not yet reached equilibrium, and we will end up with more ammonia when we finally reach equilibrium than we have at this time. We will have less dinitrogen and less dihydrogen than we have at this time. This is what the mass action expression can let us check. And this is how we can find it for every reaction based on the balanced reaction. As to the KEQs, they will have to be provided. There's no way to look at a reaction and know what the KEQ is supposed to be. So they would be either calculated because you know you're at equilibrium, and your Q at equilibrium is your KEQ, or they will be provided from previously known reactions. This reaction will always have this KEQ. Does not matter how much of each reagent you throw in to start. Dinitrogen plus 3 dihydrogens going to 2 ammonias will always have the same KEQ at the same temperature. They are temperature dependent. That is the only thing that changes their values.